Hello, this is Math Jazz from Almost Cool, and for today's live stream, we are going to be talking about matrices. We talked a little bit about matrices on Tuesday last week, but we'd like to just review a little bit about matrices as we go. If you have any questions that you'd like me to answer, then please email them to mathjazz9@gmail.com. The or you can type them into chat. So actually, do I have my email address in the description of the video? Yes, I do. Okay. So it is there for you to use if you need it. Anyway, so today we're going to be talking about matrices. So, um, let's swap over to our camera. Now, recall that a matrix is a rectangular array of numbers. So, it's not just a list of numbers, it's a list of lists of numbers. We usually put either square brackets or round braces around them. So this is a 2 by 2 matrix. And so this is a 2 by 2 matrix because it has 2 rows and 2 columns. So 2 rows by 2 columns. So we call it a 2 by 2. On the other hand, if we increase the number of, this would be 1, 2, 3. This here is a 2 by 3 matrix. So the first number refers to how many rows, the second one refers to how many columns. Now, we already talked about row reducing a matrix, so we can use row reduction to find solutions to equations. For example, if this were representing a system of equations, it would be 1x plus 2y equals 3. 4x plus 5y equals 6, and row reducing this matrix will find the point where these two lines intersect each other. We'll do that now. So to row reduce this matrix, I'm going to kill off this 4 by subtracting 4 times the first row from the second row. So the first row will not change in this step. 4 minus 4 times 1 is 0. 5 minus 4 times 2 is 5 minus 8, which is negative 3. 6 minus 4 times 3, 4 times 3 is 12. 6 minus 12 is negative 6. So that's the first step in row reducing. The next is really up to you. You can either kill this 2 off, or you can divide this second row by negative 3. I'm going to choose the second of these options because there's the numbers work out nicely that way. But if I did that, I would get the matrix 1, 2, 3, 0, 1, 2. I just divided all of the entries in the second row by negative 3. And then I'm going to subtract 2 times the second row from the first. So I get 1. I'm not changing the second row at all. But 2 minus 2 times 1 is 0. And 3 minus 2 times 2 is negative 1. So I claim that the point, if this is my x column, this is my y column, I get 1x equals negative 1. So that's x equals negative 1. And y equals 2. That's the solution to my equation. We can plug that into our equations here to check that. So we get negative 1 plus 2 times 2 equals 3 is what happens when I plug these points into these equations. And I get 4 times negative 1 plus 5 times 2 equals 6. Let's see if these balance. Well, 4 minus 1 is 3. 10 minus 4 is 6. So I found the correct solution to my linear system. Okay, so from there, reminding about row reduction. Row reduction is actually, I think, not the easiest thing to do with matrices. So, um, if I were coming up with curriculum, I'd talk about how to add and multiply matrices first before talking about row reductions, but I think I said this in my previous video that solving linear systems is about the easiest thing that we can motivate with matrices. Matrices can solve all kinds of problems, but some of these problems are hard to state, and maybe would take a bit too much background information to understand what the question is before introducing the matrix as how to solve it. Whereas by the time you're learning about matrices, you've usually had to solve several linear systems. So this is a problem that you've already seen before, that you have an understanding of, and the matrix is a tool that also solves this problem, and that's kind of the path that our textbook has taken this semester, is to introduce matrices as an alternative way to solve linear systems, and then going from there to use the matrix to do other things. So, with that, what I'd like to talk about is probably the easiest thing we can do with matrices is addition. So, you can only add matrices that have the same dimensions. So, since our examples up here were a 2 by 2 matrix and a 2 by 3 matrix, it is not possible to add them. The statement, well, there's no agreed upon formal accepted way to add matrices of different dimensions. But if you do have matrices that are the same dimensions, like the 2 by 2 matrix we had earlier, 1, 2, 2, 3, and we're adding another matrix, let's say -3, 1, 3, 2, then you add them component-wise. You take this is the 1, 1 entry, therefore it's 1, 1 because it's in the first row, first column, and you add it to the 1, 1 entry here, and you get 1 minus 3 is -2. You do the same thing. This is the 1, 2 entry. This is the 1, 2 entry. So 2 plus 1 is 3. 2 plus 3 is 5. 3 plus 2 is also 5. So this is how you add matrices. And the bigger they are, the longer it takes, but it's not that much different from regular addition of regular numbers. Okay, so the next thing is, let's talk about scalar multiplication. Okay, so scalar multiplication is what happens if we have some number that we want to multiply by our matrix. So we have a matrix 1, 2, 3, 2. Well, the way that we do scalar multiplication is that we're going to multiply one row, and we can pick any row, or one column, and we can pick any column, and multiply by that number. All right, correction. You multiply all of the entries by that number. So 3 times 1, 2, 2, 3 is going to be equal to 3, 6, 9, 6, because we have 3 times 1, 3 times 2, 3 times 3, and 3 times 2 again in our multiplication. Okay. Okay, so scalar multiplication isn't so bad, and addition isn't so bad either. However, if we have to multiply matrices together, this is where we start getting some complications. So let's suppose that we have a matrix, and we're going to start small. Here's our 1, 2, 2, 3 matrix. We're going to multiply it by the other 2 by 2 matrix. We have -3, 1, 3, 2. So the way that we multiply matrices is we're going to take the first matrix rows. So here are the 2 rows of the first matrix, and we're going to multiply them by the columns of the second matrix, like so. This is the first element of the first row. This is the first element of the first column. We're going to multiply those together. -3 times 1 gives us -3. This is the second element of the first row. This is the second element of the first column. We multiply those together and add them to what we already have. And we would keep going all the way across the top row until we hit the end, and keep going all the way down the first column until we hit the bottom, doing this process. Once we do that, we are done with the first row, first column combination. We move on to the second row, first column. So 2 times -3 is -6. 3 times 3 is 9. Add them together. Then we go to the first row, second column. 1 times 1 is 1. 2 times 2 is 4. 2 times 1 is 2. 3 times 2 is 6. We have now run out of all combinations of these rows with those columns and put them accordingly. We let the row of the first matrix determine which row we're putting the answer in, and the column of the second matrix determine the column that we're putting it in. So, for example, the -3, 6 is in the 1, 1 position because it came from the first row and the first column, whereas the 2, 6 is in the 2, 2 position because it came from the second row and the second column, so on. Okay, so with this, we now simplify. 6 minus 3 is 3, 9 minus 6 is 3, 2 plus 6 is 8, 4 plus 1 is 5. This is the matrix that we get from multiplying this matrix by this one. So, you might be wondering, what's a geometric interpretation of multiplying by a matrix? Well, or multiplying 2 matrices together. Well, there are lots of different things that this could represent. Just like adding and multiplying could mean lots of different things in the real world. We can use addition to represent money that is being paid into an account. We can use addition to represent how far something is driving, and we're adding up all of the miles as we're going. We could use multiplication to say find areas of shapes. We can use multiplication to figure out production of a good when we know the rates of productions for our workers and how many workers we have. So there are lots of different physical interpretations that addition and multiplication can represent. Now, what's a good physical representation of a matrix, or of matrix multiplication? Well, so this is what I have for you, and this is one thing that we can do with a matrix. What we can do is we can represent stretching, shifting, rotating the plane as a two-dimensional matrix. So we're just going to use this 1, 2, 2, 3 matrix. So this represents rotation and a shift and a stretch. Some sort of deformation of a flat two-dimensional plane. Okay, so we have some sort of two-dimensional rubber sheet, and we're going to do some sort of rotation and stretching and shifting of it. Okay, so this two-dimensional sheet of rubber might be stretched so that, you know, this axis gets pulled this way on a diagonal. We've rotated it a little bit, and this one gets pulled like this. So basically everything is being pulled this way and compressed in that way, kind of like what would happen if you grabbed a rubber sheet from one side here, and pulled outward. Okay, so I'm not going to... There are ways of looking at a matrix and decomposing it into its pieces. You know, taking a matrix and breaking it apart into, this is what rotation it does, this is what stretching it does, and this is how much it shifts a point from one point to another. There are ways of doing that. We won't be getting into that in today's live stream, but all that we'll worry about is this represents some sort of deformation of a two-dimensional plane. And now this one-dimensional matrix represents a point x, y that's on the plane. So it's some point, here's a point x, y on the plane, and when we multiply by our matrix, what we'll get is where the point ends up after this deformation. Okay, so here's the point xy, and maybe this is where it ends up after we multiply by our matrix. So this point gets shifted up there after all of the stretching occurs. Okay, so let us see how this works on a concrete example of this. So let's pick a specific point. We're going to pick the point x, y, there's no line there, equals 1, 2. And again, there's no line between the different rows of a matrix. So that point on our plane is the point 1, 2 here. And so we're going to multiply out our matrix. So we have 1, 2, 2, 3 times 1, 2. We go 1, 2 times 1, 2 is equal to 1 times 1 is 1, plus 2 times 2 is 4, and then 2 times 1 is 2, plus 2 times 3 is 6, and that is going to equal 5, 8. So this is our new point, 5, 8. So 3, 4, 5, and 8's way up here. I'm going to put it up here. Here's the point, 5, 8. Now what's interesting is that we can join a whole bunch of points together. 1, 2, 2, 3. Here's the point 1, 2. I can put another point -1, -2, and I can put another point 1, 5, and I can list all of the points that I need, and multiply by this matrix, and what's going to happen is I'm going to get a new matrix where this will be 5, 8, because the first point was 1, 2, so the first point in the product is going to be 5, 8. And as I, go and multiply this whole 2 by whatever length matrix, whatever length by 2 matrix. No, it's a 2 by what? It's a 2 by something because there are 2 rows. Rows come first. So it's a 2 by something matrix. When I do this multiplication, I will get a list of points, 5, 8, and then another one, and another one, and another one, all the way down. And all of these points will correspond to what happened to these points after the transformation occurs. So 1, 2, we get 1 times 1, -1 is -1, 2 times -2 is -4, so I get a -5, and I get a -2, and a -6 is a -8. That makes sense because this is the negative of this point here. 1 times 1 is 1, plus 2 times 5 is 10, 1 plus 10 is 11, 2 times 1 is 2, 3 times 5 is 15, 2 plus 15 is 17, and so on. And you're wondering, well, why do I need to be able to figure out where a whole bunch of points go quickly in a deformation? Well, it works with 3 dimensions too. If you take a 3-dimensional matrix, then you can multiply 3-dimensional points. This will be a 3 by 3 matrix. This will be a 3 by something matrix, something being the number of points you have. 3 being because in three-dimensional space, your points have to have 3 coordinates to them. So if you have 3-dimensional list of points that represent, say, all of the points of a character in a 3D movie or a 3D video game, all of the points that represent where all of the little polygons are that represent the boundary, the surface, the skin, the model of your 3-dimensional character or 3-dimensional object, then your matrix that you're multiplying by shows you where all of those points have to move in the computer to accomplish whatever task you're trying to do, whatever deformation you're trying to do. So I said you can take a matrix and break it apart into its different parts, its rotational part, its shifting part, its stretching part, and so on. But you can also build up a matrix from specific forms. There's a form that will give you a rotation of a certain number of degrees, and without looking it up, I might remember it. I'm pretty sure it goes, if you want to rotate your object by theta degrees, then it's I think it's sine theta, cosine theta, cosine theta, negative sine theta. And multiplying a point xy by this will rotate your, here's your point xy, and it will rotate it around theta degrees until it gets to its new position here at new x and new y. So it'll rotate around to the origin. There are ways of modifying this so that the center of your rotation is, the axis of your rotation is wherever you choose it to be. But this is a use for computer animators, is they can define their character by a list of points and then multiply those points by matrix after matrix to get each new frame of the movie or each new frame of the video game. This is exactly how animators do that, and whether they're working directly with multiplying the matrices or whether they have a program that converts some other form of input into matrices that then render into the video, it doesn't particularly matter. This is the method that happens at some point in the process. In fact, in one of my computational physics classes, we had to animate a little solar system and had it rotating around a sun, and we did that all via multiplication by matrices. But I I feel that most animators use Maya instead to do that process. Anyway, this was our live stream today, and I hope that you learned something about matrix multiplication, and we will see you next time, where we will talk more about matrices and using them to solve problems. So, um, I hope you enjoyed the live stream, and we will see you Thursday. Bye.